Welcome to lesson 1.7. We're talking about combinations of functions and composite functions. This is stuff we talked about in Algebra 2. Obviously, the composite functions, I think, were a bit challenging, so we'll get a little redo on that. Hopefully that is now good. Objectives, we're going to find the domain of a function. We're going to combine functions using the algebra of functions specifying domains, so add, subtract, multiply, divide. Then we're going to talk about composite functions, and then we're going to talk about domains in relation to composite functions, which is why we're talking about it at the beginning as well, and then write functions as compositions. All right, finding a function's domain. Basically, it's the values of x that work, right? Anything that you can substitute in for x and get a real number is part of the domain. So things that, basically the two things that you're looking for are the fact that you can't divide by 0 and the fact that you can't take a square root of a negative number. All right, so if you're finding the domain of 5x divided by x squared minus 49, we're really just looking at the domain. X squared minus 49 can't equal 0, right? So that means if x squared minus 49 can't equal 0, that means x can't equal 7 or negative 7, okay? If you were to write the, so yeah, you can just solve it like x squared minus 49 equals 0, add 49, take a square root, and it's plus or minus 7. If you're writing it as an interval notation, the way that you would write that is in 3 separate intervals, you have a whole at negative 7 and then a whole at 7. That's why we're using parentheses here to disclude negative 7 and 7. All right, now we're talking about the algebra of functions. So adding, subtracting, multiplying, dividing. These notations are essentially interchangeable. Basically, if you're having f plus g of x, it's just taking the f function and the g function and adding them together. Same thing with subtraction, same thing with multiplying, same thing with dividing. Again, you can't divide by 0, so you have to have the caveat that g of x can't equal 0. So if we have two different functions here, the f function and the g function, f plus g is just simply adding those together. You collect like terms. In this case, it would just be the constant. You have x squared plus x minus 6. The domain has no restrictions, right? Because there's nothing that's being done here. You're not dividing. There's no square root. So there's no restriction on the domain. So the domain is all real numbers, and that's how you would write it in interval notation. Okay. Let me go back for a second. Essentially, that would be true for subtracting and also for multiplying, assuming neither of the given functions at the beginning have division or a square root to begin with. If you are dividing, if it was like f of x divided by g of x, then you would need to figure out what values would make g of x equal 0 and then disclude those from the domain. All right, so composition function, that's where we're using the symbol. That's a little circle. It's not multiplication. Interchangeable with this notation where it's the g function inside the f function. I prefer the second way it's written, but you need to know both because it could be written either way in any of your practice questions. The domain of the composite function f of g is the set of all x such that x is in the domain of g, so the function that's going on the inside, and then g of x is in the domain of f, meaning that you have to make sure that what you're substituting in to the f function doesn't then create one of the situations where the domain would have a break, such as dividing by 0 or square root of a negative. So the first part here is just forming the composite function. You have the f function, you have the g function. F of g of x is where g goes inside f. So you're going to, apologize, you're going to take the g function and substitute it inside the f function. So it's 5 times x is now all of the g function. Did it again. So it's 5 times 2x squared minus x minus 1 plus 6. You just simplify that, distribute the 5, collect like terms. So now you've got your new function. All right, that's f of g of x. If it was g of f of x, the 5x plus 6 would go in for the x in the g function. Whatever's on the inside is what goes inside. That's how I remember. Okay. It's even a little more obvious when you're using this notation. What's on the inside goes inside that function. All right, the following values must be excluded from the input of x. If x is not in the domain of g, it must be in the domain. It must not be in the domain of f of g, meaning if the function that's going inside, if you can somehow make that undefined, then you can't substitute that into the f function. So anything that makes the g function, the function going inside, undefined would be excluded from the domain. And then any x that you would substitute into the g of x, that when it gets substituted into the f, that makes the f function undefined, needs to be excluded as well. So let's look at that in action. Here you have two functions, f and g. You're also, again, doing f of g, meaning g goes inside f. So here we're looking at the g function going inside the f function. What you end up with is, well, you end up with 4x over 1 plus 2x. Okay. Essentially, what you can do is multiply by x over x. That you can't have a fraction in a fraction. So multiplying x by 1 over x gets you 1. Multiplying 2 by x gets you 2x. Multiplying 4 by x gets you 4x. So that's how you end up with 4x over 1 plus 2x. Right. So now we found our composite function. Now we're going to need to find the domain on the next slide. Okay. So g of x cannot be undefined. What would make this undefined? Well, the denominator is simply x, so that means x simply can't be 0. Okay. And then when we look at the composite function, well, what would make it undefined? Well, it's whatever would make 1 plus 2x equal to 0. So if you set up 1 plus 2x, set it equal to 0, that's what x can't be, right? So you subtract 1, you divide by 2, and x can't equal negative 1/2, right? So again, you're looking at the g function, whatever's going on the inside if it's not g, but in this case it's g. And then the composite function, what makes either of those undefined? In this case, we have 0 and negative 1/2. So when you write the interval notation, you've got to break at negative 1/2, and you've got to break at 0. Right, when you form a composite function, you compose two functions into one. That's why it's called a composite function. You're combining them, you're composing them. You can go the opposite direction. You can take a function and decompose it and write two functions as a composite function. So in this case, you have h of x is equal to square root of x squared plus 5. The f function, one of the functions would just be square root of x. The other function would be everything that's inside. So you have x squared plus 5. Then h of x is equal to the composite of f of g. That's it. So obviously, you're going to see some different things when you get to the practice. Running through this lesson, we just really saw like one example of each thing. We're going to have plenty of time, well, you're going to have all the time in class to work on the practice once you're done taking the notes. So please ask me questions if you have questions. You can ask me questions while you're taking the notes, or you can wait till you get to the practice and see if there's something you don't know how to do. And then please don't hesitate to ask me questions. We'll also be doing this in class. We'll be doing the practice for 1.7 in class tomorrow, and then we'll just do when we get back after SLC. Okay. Again, let me know if you have questions.